All 5 of the primary aberrations leave a noticeable fingerprint on an image. The first 3 aberrations leave a blurred point of best focus. But Petzval and distortion move the location of the point of best focus. Petzval moves the best focus point off the image plane, and distortion moves the best focus point to a new location on the image plane. As with the other aberrations, distortion comes in a positive and a negative form. Positive or pincushion distortion causes lines that are straight in the object to bend inward in the image while at the same time making the image larger. With negative or barrel distortion, straight lines in the object bulge outward while at the same time making the overall image smaller. Positive distortion occurs in zoomed-in telephoto lenses. Zoomed-out lenses can exhibit negative distortion, with the most extreme case of negative distortion probably being found in wide-angle lenses. Each term in the wavefront expansion corresponds to a different aberration, and each term has some coefficient, W sub 311 for distortion. More about this expansion after I make the counterintuitive point that if this coefficient is negative, then to third order, distortion is positive. Positive distortion is so called because points in the image move outward. What should be a rectangle in the bottom left image has each of its points relocated to points that are radially farther out, with the opposite being the case for negative distortion. The farther a point is from the center of the image, the larger the displacement usually. So distortion is a variation in the magnification with distance from the center. When both positive and negative distortion are found in an image, the result is mustache distortion. How does mustache distortion alter an image? Well, it doesn't do it this way. Instead, straight lines are curved into something that sometimes resembles, well, a handlebar mustache, with points in the center of the edge possibly moved outward and points nearer to the end of the edge possibly moved inward, giving Mona Lisa wide shoulders with small hands and a small head. Just as a fine print disclaimer, features in PowerPoint were used to generate the suggestion of how mustache distortion could change Da Vinci's most famous lady, and I'll keep doing my artist conceptions by imaging this candlestick through this ridiculously thick biconvex converging lens. Follow this ray from the dripping wax on the object to the dripping wax on the image. Follow another ray from the tip of the flame on the object to the tip of the flame on the image. If you look carefully at the image, you'll notice that the flame is more compressed than the candlestick. That's negative distortion. Now illustrating this with a diverging lens, the image is to the left of the back surface. These rays were traced in OpticStudio, not PowerPoint, and here too distortion is visible. The flame is stretched compared to the candlestick. That's positive distortion. For thick singlet lenses, a positive biconvex lens results in negative distortion, and a negative biconvex lens results in positive distortion. And meniscus lenses tend to do the opposite. As soon as there's anything other than one thick piece of glass, either type of distortion is possible. And thick is the operative term here. If the lens has no thickness, there'll be no distortion. Distortion is due to the fact that a chief ray emerges from a lens in the same direction, but at an altered height. The larger the field angle, the larger the deviation in ray height. Wavefront error is expressed to fourth order in this expansion, with each term representing a different monochromatic aberration. W is the optical path difference between the actual wavefront and an ideal spherical wavefront. This wavefront error accumulates over all the surfaces in an optical system. Y and rho are the normalized image height and exit pupil coordinates respectively, and theta is the angle between them. Each term in the wavefront error expansion includes the variables y, rho, and cosine theta, along with an aberration coefficient. If the combination of y and rho powers add to 4, then the term is a third-order ray aberration. Higher-order aberrations have higher powers of y and rho, which add to this expansion to result in what is often a non-monotonic variation of wavefront error with these coordinates. The first term is the innocuous piston. The second term is spherical aberration, followed by field curvature, astigmatism, and coma. The last third-order term is distortion, which varies as the height of the image cubed. So the wavefront error due to distortion is W sub 311 times y cubed rho cosine of theta. The expansion coefficients are related to the Seidel coefficient simply enough, and these 5 aberration coefficients are referred to as the Seidel aberration coefficients and are useful for computing the contributions of each aberration to the wavefront error. Distortion can be described both in the image, which is easy, and in the pupil, which is kind of abstract. And it's helpful to describe distortion in the pupil because W sub 311 has a physical meaning in the pupil. The reason why the image point ends up in the wrong place is because the wavefront in the pupil is tilted, which then sends the ray to the wrong spot on the image plane. The separation between the edge of the tilted wavefront and the edge of the wavefront that would send the rays to the correct point is minus the wavefront aberration coefficient times y cubed. W sub 311 is related to the distortion in the image through some fairly simple geometry. The tilt angle of the wavefront is also the tilt angle of the rays, and the tilt angle of the rays is approximately dy, the location error of the chief ray, divided by f, the focal length. Well, it's actually divided by the distance to the image point, but that's very close to the focal length, so let's just use it. So back to the pupil. Just inspect this arc length. The tilt angle is also W sub 311 times y cubed divided by the pupil radius. If you want to know what dy is for a point not at the edge of the image, the wave is tilted by some angle that's smaller by a factor of dy cubed. So there you go. Rearrange this expression for dy, toss in these factors of 2 so that the f number can be used. And this is the transverse ray distortion, the distance that the chief ray moves in the image plane. This does include y cubed, where y is the normalized height in the image. The maximum distortion refers to the distortion where y equals 1. So I'll use this expression to find the maximum distortion. To measure the percent distortion, I'll superimpose the pincushion outline on a hypothetical square image sensor. Here I asked OpticStudio to make a grid distortion plot of a thick biconvex singlet with an aperture stop in the back. A perfect square grid is imaged through the lens. A little vector arrow shows the displacement of each crossing point on the grid. The corners define the image height, with the diagonal being twice the image height. The displacement of the corner determines the max distortion, which is the ratio of the corner displacement divided by the expected corner location. Using the values that I measured directly off the screen, I find that the max image distortion is positive 8.97%. Compare this to the value of 8.92% displayed in the information field on OpticStudio, which isn't bad for just moving a cursor around the screen and reading off coordinates. Another distortion metric is Standard Mobile Imaging Architecture, or SMIA-TV distortion. This is a more direct measure of the distortion since it uses the deviation between two real points in the image rather than the deviation between a real and an ideal point. Television viewers are able to immediately perceive this measure of distortion. If it's too small to perceive, then the non-uniformity of magnification throughout the image will be too small to perceive. I read the values for the deltas and the length of the center of the image right off the screen, put them into this little expression, and got 4.56%. Compare this to 4.5% in the OpticStudio information block. The magnification throughout a distorted image is non-uniform. In fact, it depends on the square of the image height. The lateral shift in image location varies as the height of the image cubed, and this changes the magnification. So I'll call m sub dist the magnification with distortion present. With distortion, the height of the image points isn't just y, but rather it's y plus dy. Insert the expression for dy into the magnification, and now it would seem that the magnification varies with image height cubed, but no, factor out the undistorted magnification, y divided by h sub 0, which is constant, and you're left with a quadratic variation of magnification with height on the image plane. And that's why distortion is called a quadratic magnification error. By the way, tilting the spherical surface of a lens introduces a magnification change that's the same at all heights in the image. So in that sense, distortion is like tilt aberration, except it's a different tilt for each angle. Or rather, distortion is a field-dependent tilt. Let's unpack the Seidel coefficient for distortion, which recall from the table that I showed earlier is twice the wavefront aberration, W sub 311. The aberration needs to be calculated one surface at a time. In this expression, the U's are the ray angles before and after the surface. A and A bar are the refractive invariants of the marginal ray and chief ray. Their values don't change as a ray crosses a surface. This script L is the Lagrange invariant, which doesn't change at all for a ray as it propagates through the entire optical system. Y and Y bar are the marginal and chief ray heights respectively. Now there are two terms in this Seidel coefficient for distortion. The first term is the Petzval curvature. The second is the astigmatism, although it can easily be reorganized so that it's spherical aberration. So I'll summarize it by saying that distortion depends in some way on each of the other aberrations, and this can make distortion difficult to control. I'll illustrate how distortion can be connected to other aberrations, and it's easiest to do with Petzval. A bundle of rays arriving from a field angle, theta, will find their focus at a point not quite on the flat image plane. The larger the field angle, the farther off the flat image surface the image will form. It'll form perfectly, but not on the image plane. That's Petzval curvature of field. The arc length from the zero field vertex out to where the image forms is f times theta. If you unroll this arc length and lay it on the flat surface, it'll look like this, but the light doesn't arrive there. It arrives here, at a slightly different location. A close-up reveals this mislocation, in this case farther out, making positive distortion. The image is unblurred on the Petzval surface, but not necessarily on the image surface. If there's any blur at the edges of a distorted image, it isn't due to distortion, but rather to field curvature. It's only the actual mislocation of the image point that's described as distortion. This is a YNU spreadsheet that I described in my video on stop shifting. The table at the bottom shows the Seidel coefficients for each aberration. Distortion can be computed using the S5 Seidel coefficient and can also be written in terms of the Petzval and astigmatism or Petzval and spherical. The Seidel coefficients calculated by OpticStudio can be compared to the spreadsheet, drawing attention especially to the distortion coefficient. You can see how close the equation comes to a real ray trace. The maximum distortion can be computed as a percent using this paraxial ray trace, and we get minus 2.34%. A positive Seidel coefficient means a negative third-order percent distortion. So a positive Seidel coefficient means barrel distortion. A negative Seidel coefficient means positive or pincushion distortion. OpticStudio makes these plots of the percent distortion on the horizontal axis against the field on the vertical axis. It's the percent distortion at the farthest field that's computed here in the spreadsheet. Now, an aperture stop has a significant effect on distortion, and this spreadsheet looked at the case of a stop in front of a singlet lens. It's more complicated with the stop behind the lens because I have to figure out where the chief ray strikes the first surface. This was covered in my stop shifting video, and this gray box is where those calculations are happening. With the stop 5 mm behind the lens, the max distortion is positive 2.46%, or plus 2.58% is computed by OpticStudio. And again, the Seidel coefficient can be compared to OpticStudio, drawing attention here to distortion and showing good agreement. This calculation was done for a 10-degree half field of view. So I was curious, if I varied this field of view, could I replicate this distortion versus field plot that OpticStudio generates? So keeping the stop 5 millimeters behind the lens, I varied the field, tabulated the max distortion percent, and graphed it. The plot on the left is from the YNU spreadsheet. The plot on the right is screen grabbed from OpticStudio. The point here isn't that you don't need lens design software or that I'm some kind of skilled computationalist. I'm not that. The point here is to encourage you in your own endeavor to know what your engineered software calculates, how it calculates it, and what it means. If I can do it, then you can do it. And here's a quick look inside my spreadsheet. I'll go through the stop and front model because that's a little more straightforward than the stop and back model. The green cells are data that are entered, and the black cells are formulas. The first column here, column C, is the object surface, surface number 0. I'm doing an object at infinity, so the thickness is a very large number. The index is 1 for air. Marginal ray height is set to 10 millimeters and an angle of 0 degrees, meaning it's coming in parallel at a height of 10 millimeters. Take that to mean an entrance pupil diameter of 20 millimeters. So the chief ray angle is calculated from the field of view, and the field of view is given way over here in cell I13. That's 10 degrees. There it is in radians. The rays proceed to the stop, surface 1, which has curvature of infinity, and a distance of 5 millimeters to the lens. The height is still 10 millimeters above the optical axis, and that's just a straight line extrapolation from what it was at the object. And the angle is the same because nothing's been done to refract the light yet. The refraction angle is used to calculate that when the refraction happens. The chief ray is forced to be 0 at the aperture stop, and it has the same angle. So the front surface of the glass is surface 2 with a radius of curvature of 30 millimeters, and the glass has a thickness of 5 millimeters. Surface power is then calculated. That's still at the same 10 millimeter height. U prime is the angle after refraction, and that's calculated from the refraction equation. The chief ray as well has a new height, a straight line extrapolation from the aperture stop to the lens, and then it refracts. U prime is the angle after refraction, and the refraction equation is used to find it. Then the ray propagates through the glass to the back surface, surface 3, which has a radius of curvature of minus 30 millimeters. And all of these calculations are done again using the transfer equation and the refraction equation for the rays. The chief ray, marginal ray, and Lagrangian variance are calculated at each surface. And then the aberration coefficients are calculated at each surface, focusing here on distortion. The distortion at the front glass surface is calculated from using astigmatism plus Petzval curvature Seidel coefficients, then scaled by the ratio of the invariance. And it's done at the back surface as well, and then they are added together to give the total distortion coefficient. The wavefront aberration coefficient for distortion is calculated using cell C23, which is the Seidel coefficient, divided by 2. Then the transverse ray distortion is computed from the wavefront error, and from that the max distortion is computed as the fraction of transverse ray distortion divided by the chief ray height at the maximum field, which is here in cell I15, and is a straight line extrapolation of the chief ray from the back glass surface to the image. Where the image is determined using the refraction equation to find out where the marginal ray reaches the optical axis. Okay, well that's how the spreadsheet determines the maximum distortion percent. So here's a little summary. A converging biconvex singlet with a stop behind the lens will have positive or pincushion distortion. A stop in front of the lens will give negative or barrel distortion. If there's no stop, a converging thick lens has negative distortion because in that case the front surface acts as a stop and it's a stop in the front of the system. Negative distortion results from forcing the chief ray to strike each surface at a slightly higher point than it would if the lens had no thickness. And if the lens has no thickness, then the distortion is 0. Finally, there's mustache distortion. which occurs in some compound lenses. Here's a camera viewfinder where the aperture stop is in front of everything. And you'll notice the variation in the sign of the distortion, positive at closer in fields, negative at farther out fields. Hybrid distortion is usually seen in well-optimized systems, especially those with higher order aspheric surfaces, because as you can imagine by looking at the graph, it hugs the zero distortion line, meaning that when there's hybrid distortion, the distortion is mostly balanced and there's usually then a lot less distortion. When the distortion is hybrid, it becomes evident that the max percent distortion isn't quite as simple as computing the distortion percent at the farthest field. Without hybrid distortion, sure, the farthest field is where the distortion is the maximum, but what's really meant by maximum distortion is as shown here, the difference between the most negative distortion, which here is 0, and the most positive distortion. Or in this example, where there's both negative and positive distortion, the difference between the two extremes. What's not helpful here is relying on an analytically computed Seidel coefficient. In fact, both of these examples had very large values of the Seidel coefficient, which is just a third-order wave aberration corrected for the stop, shift, conic, and fourth-order aspheric surfaces. But that isn't everything that goes into the image plane displacement of a chief ray. These real distortion plots are the result of a ray trace, which is affected by all orders of aberration. Distortion doesn't show up in spot diagrams or ray fan plots. In most software applications anyway, these are a reference to the location of the chief ray, but it's possible to see the influence of distortion in a ray diagram. Compare the relative heights of the various fields' ray bundles in object space and in image space. Notice how the outer field is moved closer to the intermediate field on the image plane. These computed ratios of outer to image field heights makes that point. And you can compute the percent distortion right from this ray trace. You only need to know one more thing. Go to the Analyze tab in OpticStudio, pull down Reports, and select System Data. In this report, you'll find the paraxial image height. This turns out to be the height where the image would have formed if there were no distortion, and here is 46.188 millimeters. So sketch that into the ray diagram, and now you have the information needed to calculate a maximum percent distortion of minus 22.7%. Just to make sure that is right, I'll pull up a distortion versus field plot, which confirms that the percent distortion at the farthest field is minus 22.65%. Distortion occurs when the optical system is not symmetric about the aperture stop. Even by itself, a thick lens lacks this symmetry because the aperture stop is the front surface of the lens. A remote stop is even more of a symmetry disruption, leading to even more distortion. The sign of the distortion of a singlet lens depends on whether the stop is in front of or behind the lens. So what happens if these two lens aperture stop systems are combined into one system? The result is called a periscopic lens, and it looks like this. These two lens elements and the aperture stop between them can be combined in such a way that there's no distortion. At 0.03%, this finite conjugate periscopic lens has virtually no distortion. Achieving this required a symmetric arrangement with the stop midway between the lenses. The lens separation is such that the magnification is 1, the field of view is not large, and the rays are two-sided telecentric. Okay, these are a lot of ingredients, all of which help to make the distortion nearly zero. But you don't always want distortion to be zero. Case in point is scanning lenses. Look at how the chief ray enters a singlet thin lens at an angle theta and arrives at the image surface at a height f times the tangent of theta. A graph of y versus theta will be noticeably nonlinear, but a graph of y versus tangent of theta is a straight line with the slope equal to the focal length. If the lens is fairly thin, then the distortion is fairly small. But suppose your goal is to convert theta, not tangent of theta, into the image height. Then low distortion actually is not what you want. To see if the image is where you want it to be, look at the F-theta distortion instead. This considers the deviation of the real image point not from F tangent of theta, but rather from F-theta. You won't usually want to do this unless you're designing a scanning lens. With a scanner, there may be a mirror that rotates an angle theta, and the image location hopefully shifts by the same angle. But it won't. It'll move some distance that depends on tangent of theta. So some effort goes into designing an F-theta lens which displaces the image point in an amount that is proportional to the angular rotation of the mirror. Now y is linear in theta. This is barrel distortion because no matter what, theta is always less than tan theta and the image point is lower than it would be with most lenses. Whether you take the F-theta or the F-tan theta view of distortion depends on whether you're designing a lens for an imaging array that collects all light at once, known as a staring array, or if you're designing for use of a scanning array, such as the photocopier. In the event of a scan lens, where the image height should track the object field, OpticStudio has an option for plotting the distortion as F-theta, such as shown on the right, instead of as F-tan theta, such as shown on the left. These data are from a lens with a lot of barrel distortion, which actually ensures fidelity when the image is being formed with scanned light. Thanks for watching.